Welcome to this deep dive into packet and protocol analysis, one of the most critical skills in network forensics. Now, we have previously discussed networks and we have also discussed several different layers starting from application, transport, network, and MAC layers. However, you can consider this as sort of a refresher because we're going to take a deep dive into packet and protocol analysis, and for that, you need to be absolutely clear about the different packet headers and how different protocols work. Before we delve into more details of packet and protocol analysis, I would just like to sort of refresh the concept of layering and the different headers and their roles. This is important to understand because in network forensics, you need to have at least a basic idea of what are the different types of headers, what are the different fields, and what role do they play in network communication. So in this example, here we have the source and here we have the destination. And then, as we previously discussed, we have different layers of the protocol stack. So first we have the application layer, then we have the transport layer, then we have the network, link, and physical layer. And every layer plays its own specific role. So at the application layer, we have protocols like HTTP, HTTPS, or DNS. And then we also discussed the concept of ports. So a port is sort of like a door through which an application communicates with the transport layer. So for example, in this case, we have the Internet Explorer application running here. It has its own specific port, which in this case is 1000. So whenever this application wants to send something to the destination, it needs to send this down to the transport layer across this port. And similarly, when this transport layer has something to give to the Internet Explorer application on the application layer, it will use the same port or the same sort of door. To keep things clean, I haven't discussed the application header. So all of these protocols, they will also have their application headers, which we are going to discuss next. Here, I want to focus more on the transport, network, and link layer headers. But bear in mind, we'll also have the application layer headers, and we'll discuss DNS header, for example, in a lot of more detail. So now imagine that your Internet Explorer application here wants to send a message to the destination Internet Explorer application. Okay, and we're going to trace the journey end to end. So you create a simple message. Let's assume that you just say hello. Now this is a very simple message and you want it sent to this application so that here the user also sees the message hello. However, before this message can be communicated, it needs to go through different layers and basically encapsulated in headers. So as a first step, what happens is that this message gets this header, this transport header added onto it. And what is transport header? The transport header basically just includes some fields. So when your packet reaches this point, this transport layer needs to know, for example, where should I send it? It may have different applications running. One may be on a different port, let's say port 500. Another application may be running on port, let's say 600. And then there is one on port 2000. So in this header, we mention what is the destination port, which is 2000, so that the destination transport layer can know that I need to forward it via port 2000 to Internet Explorer application, because you'll have different applications running on different ports. Okay, so that's why we add this transport header. But in addition, we also include the source port number. Why is that important? Because when the destination responds, and you get the packet back, you want your own transport layer to be able to decide which port to forward it up to. So for example, in addition to this Internet Explorer application, you may have other applications also running on different ports. So you want to be clear which port do I need to forward it to. This one, or this one. So that's why when you put this source port number, and when the destination responds, so it's going to say, go to destination port number 1000. That's all good for transport and application layers. But your packet is not going to directly jump to the destination. It has to pass through certain routers before it can make its way to the destination. Once your packet is within the source or the destination system, port is enough. But how to reach the destination system itself? For that, you need the IP addresses. And that's the role of the IP header. So in IP header, you say that this system's IP address is, for example, 3.3.3.3, and the destination IP address is 4.4.4.4. Okay, so you need to put the source IP address, your IP address, as well as the destination's IP address. Think of the IP address as the house address, okay? So you're saying that this is my house address and I want this letter delivered to this house address. But once this letter has been delivered, let's say there are 5 people in that house, then that's the port numbers which is going to decide, okay, which application or which person it needs to get delivered to. But before you can process the port numbers or, which person to deliver it to, you first need to deliver it to the house itself, okay? So for that, we need IP addresses. So how do IP addresses actually help? So imagine there are multiple routes. Okay, so this is a network. So imagine you have different routes in this network or on the internet, and you have other destinations as well. Okay, so for example, this could be other destinations. When these routers on the internet see the destination IP address 4.4.4, they will decide, okay, we need to go this route, okay, instead of, for example, going to this route. So IP address helps the end-to-end routing, and it also tells like which final server or computer you need to deliver the packet to. But there is one more layer, which is the link layer. And what's the role of that layer? So the role of the link layer here is to add the source MAC and destination MAC addresses. Why? Because while the IP address helps you with the sort of like end-to-end routing, for example, the end-to-end path, the MAC address basically helps you do these hops, right? This is one hop, this is second hop, and this is the third hop. Because on each link, you really need the physical address. So for example, you need to know your MAC address and this router's MAC address. Then you need to know this router's MAC address and the next router's MAC address, and then so on and so forth. So think of it like MAC addresses are used for step by step, and they will keep on changing. For example, here you've put your own MAC address. Next hop is B, for example. Okay, let's say this is B. But when router B sends it to router C, for example, it's going to change source MAC to B and destination MAC to C. And then C is going to change it again to source MAC to C and destination MAC to the actual destination. But don't worry too much about it. Just understand at a high level that we have 3 layers, okay? So MAC layer is used for like link to link routing. IP layer is used to sort of like deliver it to the end destination. And then transport header is used to sort of like within that destination or which person or which application to actually deliver it, on which port do you want to deliver it. So from another perspective, this is your actual data. However, it is encapsulated first in the application header, which resides at the application layer, and this could be HTTP header, HTTPS, DNS, or FTP. We are going to discuss DNS in a minute, but just remember this is an application layer header, okay? And this whole thing would be encapsulated in the transport header. And usually we have either TCP headers or UDP headers. We're going to discuss these headers in a minute. And then you have the network header, and finally the link layer header. Now, how would these different headers help us? Now, these headers are very useful for forensic investigation. So for example, the TCP header could indicate if someone is trying to do a port scan. A suspicious DNS header, for example, could indicate contact with a remote command and control station. Why? Because if you recall, the domain name service was used to resolve destination URL or the server host name to an actual IP address. Because the internet doesn't really understand names, it needs actual IP address. So for example, let's say your remote command and control station was this one. In order for someone from within your network to actually send to this server, they would need to resolve it to an actual IP address. Like what's the actual IP address of this server or this domain? And then you'll have something x.y.z.x, for example. So this is done via the DNS header. So by capturing DNS header and analyzing it, you would be able to identify if some suspicious communication or link is being opened to a remote server. And similarly, you can also find a lot of information from the IP headers. Now, a very common scenario, one that we have already discussed in the cyber kill chain as well, is that at the final stage, usually a malware that has infiltrated your network and your systems, it would try to basically open a remote backdoor to a remote command and control station. Okay. So basically, sometimes it's very useful to analyze the network traffic to see what are the websites or servers that have been visited. And how would you know that? So DNS is always used before actual communication happens. So for example, if you want to talk to facebook.com or maybe a remote server, an SMTP server, you still need to translate these to IP addresses, okay? And that's done by DNS. So if you capture DNS headers, you can find a lot of information. So just a quick recap. So let's say you want to communicate to this remote server. So the first step is that you'll go to DNS server and you'll say, okay, what is the IP address of facebook.com? It's going to give you the actual IP address, the resolved IP address, and then you can go and talk to facebook.com, or instead of facebook.com, this could be a remote command and control station. Now let's start with the DNS header. Once again, DNS is an application layer protocol. Okay, so remember that. So the first field is identification. So this is a unique message ID. And once you send a DNS request, you'll need to include a unique ID here. And remember, the same ID would be used in the reply so that you can know against which request is this reply. So for example, let's say you send 3 different requests for 3 different websites. So the first one may be numbered 1, the second one may have identification ID as 2, and the third one as 3. Now, the answers may be received out of order. For example, the 3 got resolved first. So when you see number 3, you're going to understand that this is against my request for number 3. The next field are flags. And this is basically just, it will mention, is it a request packet or a reply packet? Really simple. And also note that in DNS, you can basically resolve multiple IP addresses using one single request. So for example, you can include multiple questions. For example, facebook.com, mail.abc.com, and xyz.com. And then basically when the answer is received, the number would be same. So if you sent 3 requests here, you'll receive number of 3 answers. And here are the actual names that you need resolved. So it could be 1, 2, or multiple. And then here are the actual IP addresses. So for example, let's say you asked, please resolve facebook.com. Then the IP address that you're going to get here will correspond to facebook.com. And this is coming from the DNS server. And then you have the field for additional information, and it's not often used in simple queries. Okay, let's do just a bit of practice to make the concept crystal clear. So let's say you're sending this request and you're going to receive this reply. Let's just quickly fill all these fields so that you have a very crystal clear idea about how DNS actually works. So first is the unique ID. So what is the unique ID for this request so that the same ID can be sent in the reply? Because if you have sent multiple requests, you need to know which reply this corresponds to, okay? So let's say this is 0x1ab, and then in the flags, I can say this is a request or a query. So this is not an answer or a response, this is the query packet, okay? We are asking for something. And let's say we're going with a simple use case, 1 question. Number of answers, this would be filled in by the destination, so we don't care about that. And now the actual question. So you can put, for example, this is your actual query. You can have multiple queries as well. And usually in the case of network forensics, what's important is that if a malware is trying to open a backdoor to a remote server here, then they would have provided the host name of the remote server. And then that's how you can basically track that a DNS resolution was done for a malicious remote control and command station. K answer would be blank. Additional information, let's assume it's also blank. Now let's go to the response message. So the first thing you need to remember is that it's going to use exactly the same unique ID 0x1AB. And in the flags, it's going to say that this is a response. So notice here, this was query and this is the corresponding response. And this would be again 1. This is coming from here. Number of answers would be 1 because one domain was requested to be resolved. So this would be www.com. The actual question which is coming from here. Okay, it would be the same. And the actual IP address would be the actual IP address of facebook.com or the remote malicious control and command station. So let's say something like. Moving on, another important header. So DNS was at the application layer. The next layer is the transport layer. And on transport layer, we usually have either the TCP header or the UDP header. TCP header is the most commonly used one. So let's go with that. So this is the source port. So if you recall, this is the port which the source application uses to send packets downwards from application layer to the actual transport layer and then so on. And this is the destination port which is used at the destination to deliver the packets from transport layer to the application layer. So the sequence number and acknowledgement number are used to track bytes that have been sent and received. So for example, the initial sequence number is 1000. So for example, source needs to send 100 bytes. So it will put sequence is equal to 1000. This is the starting point. And then it sends 100 bytes of data. And when the destination has successfully received these 100 bytes and it knows the sequence number was 1000, so then it will say, okay, I am expecting you to send from 1100 bytes onwards. So basically it's saying that I acknowledge I have received everything 1000 plus 100 is equal to 1100. So you need to send from 1100s onwards. So this is just a way for source and destination to keep track on what's being sent and what's being received. And then we have the flags and checksum fields. So in this one, for example, checksum validates whether the packet has become corrupted or not. Next is the IP header. This is also a very important header. So the first is the version. So as you know, we have two popular IP versions, IP version 4 or IP version 6. So IP version 4 had 32-bit IP addresses. So for example, 192.168.1.1. But the issue with this one was that even though this makes up roughly 4 billion combinations, it still was less. So then we had IP version 6, which has 128 bits. And you can basically assign a unique IP to every grain of sand in the world. So we are never going to run out of IP addresses, which was an issue with IP version 4. So IP version 6 solved that issue. The next one is identification. Once again, every IP datagram, IP packet has a unique ID. And time to live is something very interesting. So what happens is that when you send a packet to a destination, so usually it's supposed to pass through a number of routers. And at each router, this time to live field decreases. We have previously discussed this as well, but just a quick recap. And the basic idea is that sometimes, because the internet is really vast and complex and all these routing algorithms are running, so sometimes packets can get stuck in loops. So if we didn't have this thing continuously decrementing at each hop, we would have billions and trillions of packets which are stuck in the loop, which would bring the whole internet down. So what happens is that even if a packet gets stuck somewhere, eventually, after decrementing to 0, it will be dropped by that router. Another use of time to live, which we have previously discussed, was to basically check the route. So for example, you want to find out what's the IP address of the next router and the next router and the next router to a destination. So you send the first packet with TTL1, it will be dropped by the first router, you will get the IP of the first router. Then you put TTL2, you will get the IP address of the second router and so on. And this is the upper layer protocol to which packet should be delivered. So remember, IP operates at the network layer. So you need to specify here, is this packet going to TCP or UDP? This is the source IP, this is the destination IP, and then we have options and padding. Now I understand the headers seem to be slightly complex, but don't worry. For any forensic investigation that we are conducting, I'm going to explain each of these important fields once again if required. But I just wanted to give this lecture so that you have sort of like a refresher of the different layers, how they connect together, what are the headers, for example, the DNS header, TCP header, and IP header, because that's what we're going to sort of see in the next lectures when we do some hands-on exercises.